Was he in the lesson?
He's not in the lesson, but he said that I must tell you to record the lesson.
He's having supper. It's okay, I'm not recording.
Okay.
And as we are. Okay, now electrical current in a clothes dryer contains two heaters, X and Y in parallel. Fig 10.1 shows the electrical circuit connected to a 230. In your home, in all your homes, we have 230 power supply. I'm sure you know that. Okay. Now, when both switches are closed, the current is what? Is that when you close this and when you close that. Calculate the power developed in the heater. Remember what I said? We said power is equal to voltage times current. So this topic you have to be good in formulas. So what is our voltage here? 230 volts. Multiplied by what is the current? 3. What do you get? Power in watts.
805.
How much? Sorry. 230.
805.
805 watts. Okay. The resistance of X is double that of what? Of Y. Determine the total resistance of X and Y in parallel. What a question. 4 marks. The resistance of X is double the resistance of Y. And we are told that determine, let's see, this, so we close the, we're saying of the resistance here, which, or whatever it is, okay? Then there is also a resistance here, okay, like this. So we're saying this resistance, maybe you can call it 2X, and this one is X. We're saying that the resistance is double. That's what they're saying. The resistance in X is the double the resistance in Y. Are we clear?
Yes, sir.
Now,
Yes, sir.
look at something here. They said when we close both, what is the current here? It's 3 point what? 3.5. 3.5.
5.
Now, can I show you something? The tricky thing that you need to know there. So because this is 3.5, the effective resistance, I want to show you something there. The effective resistance of these two resistors, we simply get it because we know the voltage, we know the current. We know that the resistance is equal to voltage divided by current. So it's 230 volts divided by 3.5. What do you get? The effective resistance contributed by these two resistors. Then we work backwards. What do you get? 230 divided by 3.5 amps. What do you get?
65.7.
60?
Yeah.
5.7.
5.7.
65.6. Is it rounded?
Yeah. Yes, sir.
Yes.
No, I don't want the rounded answer. There's a reason why I'm saying that. I want a perfect answer. What's that as a perfect answer then?
It's 65.714 2857.
Okay, I have something like this. Okay, there's a reason. Okay, let's leave it like this. Let's leave it as 230 over 3.5 for now. Okay, let's just leave it like this. Okay, we don't want to round it, or otherwise you store the actual value. Now this is our resistance, but look at this. We are saying this resistance is double that the resistor of that. So remember, how do I calculate effective resistance? I say 1 over T is equal to 1 over the resistance of X, which we agreed that we are going to call it 2X. So it's 1 over 2X plus 1 over X, because the Y is half that of that. All together, like this.
Yes, sir.
So let's do mathematically, 2 is the common denominator there. So 2X brackets. 2X into 2X, it's 1 times 1, it's 1. plus 2 into this, x into this is 2 times 1, 2, is equal to 1 over RT. Are we together? Add these two, you get what? 1 over RT is equal to 3 over 2x. But remember, this is not RT. RT is the inverse. So if you do the inverse, we get 3 over 2x. Okay. But we now know that 3 over 2x is equal to the resistance that I said leave it like that. You said 230 over 3.5.
3.5.
230 over 3.5. Now cross multiply. So we get what? 3 times 3.3. What do you get? 3 times 3.5?
You get 10.5.
10.5. 2x times that, isn't that 460?
60.
Then x is going to be 10.5 over 460.
Yeah. Okay, so that's 0.0228 26
0.0228.
0228.
Okay, like this, okay. Then the other one, okay, that's x. Then the other one is twice that resistance. How did you get them?
Yes, sir.
Okay, but you really get those tricky questions. Now, in a room, in a house, okay, there are 4 electrical lamps in parallel with each other, controlled by a single switch. With all the lamps working, one of the filaments suddenly breaks. What if, okay, with all the lamps working, one of the filaments suddenly breaks? What if anything happens to the remaining lamps? Explain your answer. What will happen to the remaining lamps? So what they're saying is that I have a switch here that is open, but this switch is controlling 3 lamps that are in parallel like this. They say 3, 4, like this. That's what it means.
Yeah, 4.
As simple as that. To simplify what they're saying, which you can think about in an exam. Okay, that's what they're talking about. So they're saying one of them breaks. Does it affect any of them? No.
No, sir.
No.
No, because they're in parallel. They will still light up. How are you together then?
Yes, sir.
Now, Fig 10.2 shows you the circuit diagram for a lamp in another room, X and Y. Okay. A two-way switch. So you've got a two-way switch. Complete the table by indicating whether the lamp is on or off for each of the following positions. Position of the switch. So if they are both on switch, will it switch on the first one? 1, 1, that's the one there. Does it switch on? Yes.
Yes, sir.
Position 2 and position 1. Position 2 on X, it means, sorry, position 1, it says, it remains like this, huh? But this one comes to where? This switch comes to this.
2.
Does it switch?
No, sir.
It doesn't switch because there isn't a complete circuit, huh?
Yeah.
I'm sure you can see that. Now, position 2 for the first one comes to that, and this one remains on position 1, does it switch on? No.
No, sir.
Tawana, are you getting it? Tawana, is it clear? Josh, is it clear what you're talking about? Josh, are you there? He's very quiet. Charmaine, can you get it, the logic behind this? Position 2, what it means is I'm moving this to that. So this is closed. I'm moving this to this. So it closes, there is complete circuit. So this is yes. I hope it's clear to all of you there.
Yes, sir.
Yes, sir.
Explain why this arrangement is useful. Why is this arrangement useful? Because it can allow you to switch on and switch off from both in two ways, or you see that in two ways, from this side or the other side. We have lost someone there. Tawana. My network seems to be a problem.
Yes, Tom.
Fig 8.1 shows you two resistors in series. We now know that we have to add two resistors in series, that and that. Complete the table only showing symbols R and I and R alone or in combination. Potential difference, it means voltage. So how do I calculate? So we have resistor, resistance, the current, and the potential difference. So if I'm given the voltage and the resistance, how do I calculate the voltage? Voltage is simply equal to I, all together. So it's I. Now this one, they haven't done this for you. They haven't found the current for you there. But they're telling you that when I multiply this resistance, I'm getting this. So what is the value? It's simply I. Because if I multiply I by that, I get 2IR. How do you get that?
Oh, yes, sir.
Then if I go back to this power, I know that power is equal to voltage times current. So if I multiply these two, what do I get? I get 2 what? I squared, because it's I times I, R. So now your formulas.
Okay.
Then you get all the 3 marks. Fig 2.8.2 shows the system used to transmit electricity from power station to a factory. So I've got this, yes, from Kariba, it's 11,000 volts power station, okay, 800 high current, power line factory, power line, okay. Now, the power station generates 11,000 volts and supplies a current of that. The total resistance of the power lines between the power stations and the factory is 1.5. Calculate the power output of the power station. Calculate the power output of the power station. We say the power is equal to voltage times current. So that is 11,000 volts, so much power, multiplied by 750. What do you get? Amps.
So you get 8,250,000.
8
million,
which is megawatts. 8 million.
250,000.
250,000 watts. All together, which is 8.25 megawatts. But you're not required to do that. How to get that? Watts.
Yes, sir.
Now,
Yes, sir.
the potential difference across the 1.5 ohms of the power lines. The potential difference. Okay. We're taught something. I think let's go back to the question. The factory, I think there's something missing. But the factory, the power there has to be 230 volts. There's to be stepped down. Power supply. Okay, that's fine. Then the resistance. Total resistance of the power lines. Okay, what do you mean? So what's the question? The potential difference across the 1.5 power lines.
Yes, sir.
Potential
Calculate.
difference is the voltage. You don't need to calculate it. It's the same. It's the answer that we got there. Okay, but potential difference now is the voltage. Huh? It's simply 11,000 volts. Huh?
V.
The power supplied to the factory. This one was the one that I was saying there's something missing. Or there has to be a step down transformer. You can't supply such high voltage to your what? I think there's something missing on the diagram.
Factory.
There's to be stepped down by a transformer. Okay, we'll leave it for now. Now, a student sets up a circuit containing 3 identical cells. So these 3 are identical. Each cell has got an EMF of 2 watts, of 2 volts. Huh? So which means combined is 6 volts. Fig 8.1 shows the cells in series, okay, that are connected like that. In terminals, uniform metal wire. Calculate the total, you see, it's simply 6 volts. So they're saying 2 volts times 3. Because they are connected in series. 6 volts. The ammeter reading is what? Is 0.25. State the name of the unit in which electrical charge is measured. What is the electrical charge measured in? Unos coulomb. Charge. Coulomb. Because we said current is the rate of flow of charge. Charge divided by time. So 1 amp is equal to 1 coulomb per second. Coulomb. State the charge that flows in what? Look at this, what we said. I told you just now that current is equal to charge divided by time. Time has to be in seconds. So now look at this. Charge is simply equal to IT, which is equal to what is our current? 0.25 amps multiplied by our time. What's the problem with the time? Is in minutes. Multiplied by 60.
60.
Like that. That's how we calculate charge.
Okay, so
what do you get? 180 coulombs.
you get, yeah, yes, sir.
Now the metal wire has a resistance of what? Of 16. Calculate the resistance of resistor X. This one here. So this one they're saying has a resistance of 16 ohms. But these resistors, look at your connection, they are in series with X. X is in series with the wire. Make sense? X
Yes,
is in series with the wire. If they are in series, we add their resistance to find the total resistance. So I'll work it from there. I'll say total resistance is equal to 16 ampere of the wire plus resistance of X. How to get that is my total
Yes, sir.
resistance. But I'm told my current reading here. What is my current reading? They say it is 3 point what? 0.25. 0.25. Which means if it's 0.25, what's the total resistance that I'm getting? Resistance is equal to voltage over current.
Current.
So it's 6 volts divided by 0.25. What do I get?
You get 24.
Which is 6 volts divided by 0.25. I get 24 ohms. So what it means is that these two are contributing 24 ohms. Makes sense now? Because they are in series. So it means 24 ohms is equal to 16 ohms plus X. So X is equal to 8 ohms.